This is chapter 9.1, a lesson on direct and inverse variation. Variation describes how two variables can be related. There's more than one way that two variables can relate to each other, and these are just two examples. The first way is called direct variation, and in direct variation, what happens is we have this constant number, this k value, that gets multiplied with one of the variables to give us the second variable. So it might look like this: y equals kx. We might also have a different variables. For example, you can have variables like f equals k times m, and various other physics equations that might also be direct variation. But the key is it's some constant number. For example, you might have y equals 2x, some constant number times the other variable, and in this case, k would be 2. Now, the key to this also is to recognize that there's absolutely no addition or subtraction, none whatsoever. So it's just a constant times the variable. We also have inverse variation, which works very much the same way, except this time we'll have this constant divided by the other variable. So it might look like this: y equals 2 over x. Or another example from real life might be volume equals some constant divided by pressure, or something like that. We'll have various variables, but the key is there's going to be this constant involved in all of the cases. Now, if two variables are directly related, then what happens is we get a graph that is a line, and this line will always go through the origin. It has a y-intercept at 0, so the line could be like this yellow line. It could be a negative relationship where the line goes down and kind of has a negative slope. And as a matter of fact, in direct variation, this constant is your slope. It's the slope, it's the rate of change of the two variables and of the line. And so, again, direct variation has a straight line for a graph. Now, if we have two variables that are directly related, and we want to be able to write an equation relating these two variables, the first thing we'll do is we'll recognize that in the problem that we are told specifically that x and y vary directly. And so if I'm told that x and y vary directly, the first thing I'm going to do is I'm going to write down my general model, y equals kx. And if it says to write an equation or to write a model that relates the two variables, I'm going to need to have x and y in my final answer. And my job right now is to figure out what is k, what is my constant of variation. Well, I'm told that x and y are 3 and 8. So what I'll do is into my generic model, I will plug in 8 for y. I don't know k, but I do know that x is 3. And once I've plugged in x and y, then my job is first to solve and find k. So I'm going to divide by 3, and that will cancel, and I will come up with that my constant is 8/3. I could write it as a decimal if I wanted to, but I'm going to keep it as a fraction. Once I have my k, then my last step is to write that equation, or sometimes we call it a model that relates the two variables. And remember, equations and models have variables, so I will write down y equals, and instead of k times x, I'll use 8/3 because that is my constant. So this is my equation, that is my model. It has an x and a y, and I've just inserted the number that k is, that I have found by using the information I have. And then part B says, now find y when x is -6. Well, I'm going to say y equals 8/3 x, and if x is -6, I'm just going to plug that right in. So y equals 8/3 times -6, and I'm going to multiply, of course, and I get that when x is -6, y is -16. Now, if two variables are inversely related, then what happens is we get a rational function. And we're going to have a graph that looks a little bit different. And what's going to happen is it's going to have two asymptotes, and it's going to have two branches that kind of curve, one like this, and then one almost reflected. You're going to have a graph that's a rational function. It has two branches, and it looks like it's a reflection of itself. And it actually has two asymptotes. It's going to have a vertical asymptote here and another vertical asymptote. And that'll actually be discussed more in the next lesson. But the idea here is it's not a line, it's a rational function. And if I'm given the information here that x and y vary inversely, then I'm going to need to write a model just like for direct variation, but this time I'm going to use the inverse variation model, k divided by x. And if I know that y is 8, then I'm going to plug in 8 for y. I don't know k, I need to find k, but I'll put in 3 for x. And now I'm going to solve for k just like I did with direct variation. I'm just using the inverse model. And so when I solve, I get k is 24. I'm not done yet because I actually still need to write my model, and my model will look like this. I will always include x and y, so I'll say y equals 24 divided by x. I'll use my k and put that in to my model. So this right here is the answer that I'm looking for, y equals 24 over x. Then what I can do is part B says find y when x equals 6. Well, if I know what x is, all I have to do is just plug it in for x, and I'll find that when x is -6, y is -4. Now it's important to understand how to write those models, because in real life we'll find that there are variables that have these relationship of direct or inverse variation. So for example, the volume of a gas in a container varies inversely with the amount of pressure. So right there, from this sentence, I'm just going to jot down my model, and instead of using x and y, I'm going to use V for volume, and it says it varies inversely, so that says K over P for pressure. That's how I'm going to write my model. But I'm not done because I need to find out what K is. So it says here that a gas has a volume of 75 cubic inches. So I'm going to write 75 in for volume at a pressure of 25 pounds per square inch. So now, just like I did in the other example, I'm going to solve for K. I'm going to multiply both sides by 25, and I will find that my constant is 1875, and now if all I have to do is write a model, I'll say V equals 1875 over P. And what this does is it allows me then to go on and solve future problems. So for example, if I know that the pressure of a certain gas is sitting at 30 pounds per square inch, and if I wanted to find the volume of that, all I would have to do is just plug in that value for pressure, and it would allow me to solve for outside numbers that I maybe don't have listed here, and I'll find that I should get 62.5 cubic inches would be the volume at that specific pressure. So that's why it's important to be able to write a model, to be able to find future values. Another example says the speed of the current in a whirlpool varies inversely with the distance from the center. So right then and there, I'm just going to pause and I'm going to say S for speed varies inversely, so K over D, the distance from the center. And for a certain whirlpool in Norway, at a distance of 3 kilometers from the center, so I'm going to start plugging things in, the speed is 0.1 meters per second. So now I'm going to write my model. I'm going to solve for K, multiply by 3 on both sides, and I'll get K equals 0.3. And from there, I'm going to write my model. S equals 0.3 over D. And if I wanted to figure out now for a distance of 2 kilometers, I could just plug in 2 for D and get my answer. If I wanted to know 1 kilometer or half a kilometer, this model would allow me to solve for the speed at that distance from the center. That's why we want to be able to write models. Now the very last part of direct and inverse variation is recognizing the relationship when we see it in and written already as a model. And so there's a couple of examples on here. They're not the easiest to see with the resolution here, but you can see that there are several direct variation equations and several that are already separated as inverse variation. And the idea here is that if we can figure out a way to write a model in the form y equals kx, it'll be direct variation. So for example, the first one is already written as y equals 3x. The second one is a little bit harder to see, but if I rewrite it like this, it's x divided by 5, I can rewrite it as 1/5 x. So now it's clear to see that there is multiplication, k is 1/5. The next example, m equals 5n, is pretty obvious to see. It's multiplication, k would be 5. This next example down here below is a little bit harder to see because it looks like inverse variation at first because x is on the bottom of a fraction. But remember, we want to solve for y. So to solve for y, I'd multiply both sides by x, and I would get it into the form y equals 2x. So that's why it's classified as direct variation. And this one is very difficult to read, but once you see it, you'll see that it is direct variation because k is 2.7. And then over on the right side, inverse variation, again, we want to make it in the form y equals k over x. And so the first one's easy to see, k is 1. The second one, though, we would need to solve for y by dividing out by x. And when we do that, we'll see immediately that yes, it is inverse variation. The next two examples are also easy to see. X is in the bottom of that expression. Once we get y alone, then it's very easy to see direct or inverse variation.
Made with Doodlecast Pro.